Before I get going, I'd like to just acknowledge some people. So thank you to Dr. Warbrick and Dr. Perry for being my advisors throughout my time on this project. Thank you to all of my lab members. Several of you are in the audience today, but you guys have been a huge help to getting all this stuff done. And there's going to be a lot of stuff in this presentation that has been a big collaborative effort. So thank you to, of course, my committee members for taking the time to be here and for all your feedback that is going to be really helpful for finishing up on the writing portion of my dissertation. And just to acknowledge that I've been funded through, we've got an NSF award and NIH award that has supported a lot of this work, and as well as Dr. Warbrick's received this Dean and Cindy Hagerman Mechanical Engineering Endowment. And some of those funds have supported me while I've been here. So just an overview of the presentation. We'll open with just some introduction to motivate what the reason we're doing this work to develop assistive robots, why we're doing that, what the Blue SABINO system is, some of its key features, talk about the design contributions I've made, some of the work that I did to develop the kinematics and force mapping for the system, and then the control system development that I worked on. And then I'll just wrap up with a summary of contributions in some areas that this work could be extended in the future. Oops. Okay, so neurological injury due to stroke is a leading cause of impairment. 13.7 million strokes occur a year, 800,000 in the US alone. And most survivors experience some motor impairment. As many as 26% require assistance in the long term with the activities of daily living like eating or drinking or cleaning. The most common long-term consequence of a stroke is impairment of upper limb and hand function. And that has major implications for the independence of survivors because we have to use our hands and our arms for pretty much everything we do. Research suggests that recovery can be increased by providing more intense and longer duration therapy, but access to therapy is pretty limited because it's labor intense and expensive to administer. So those problems have led us over the last 3 decades to be working toward development of robots that can automate different aspects of the therapy process. They can be useful for taking care of strenuous or labor intensive aspects of rehabilitation. And they can also provide precise and quantitative tools for assessment and serve as research platforms so that we can better understand the underlying mechanisms of recovery. There have been early clinical results that have given evidence that upper limb robotic interventions can result in improvements that meet and exceed traditional therapy. However, it's still pretty difficult to compare devices and therapy approaches. And that's partially reflective of there being lacking clinical data, limited clinical adoption of these different devices, and that some of the capabilities of devices that are out there are still pretty limited. So what's going on in the research end of the field at this point is we're trying to expand the numbers of degrees of freedom that these robots have and make it so that their controllers are more sophisticated and that they're capable of providing therapy and assessment at all stages of all stages of recovery and all levels of impairment. Okay, so I'm going to talk about the history and features of Blue SABINO. Blue SABINO is an acronym. This is what it stands for. It's a bilateral upper extremity exoskeleton for simultaneous assessment of biomechanical and neuromuscular output. It's kind of a mouthful. This is a system that has kind of an extensive design history behind it. These are some previous iterations of past designs, including a younger Dr. Perry working on his iteration of the device, Cadence 7. We're implementing the system in stages. We started with a 2-degree of freedom version. Most of my work has been on 5-degree of freedom version. And the vision, at least for just the arms, is to extend to 18 degrees of freedom total and have 2 different arms and a really high degree of mobility. And then you can see on the right here the progression of the 5-degree of freedom design while I've been a student here. Some special features that this system has that are kind of notable. We have these remote center mechanisms that give us lots of workspace around our arm that we can do things like attach EMG electrodes and don't have to have a motor that interferes with somebody when they lift their arm up. We're going to have this prism mechanism that allows elevation, depression, protraction, and retraction of your shoulder. That's really important if you want to do any reaching tasks that require you to lift your arm above like 90 degrees. We'll also have the capability to add these hand modules to do some reaching, some grasping interaction with objects tasks. And just overall, the Blue SABINO, we worked really hard to get a high degree of mobility in this design so that it can approach what a healthy human arm is capable of doing. Another area we worked a lot on in the system is having it be able to fit a large range of people and work well in a clinical setting. So we've got adjustments so that we can fit it to a large range of people's shoulder widths, but also so that it can come farther and maybe somebody joining. Oh, this. Okay. Yeah, so it can come farther apart and we can have somebody be wheeled into the system, basically. You work on putting electrodes on them somewhere where there's plenty of room for physicians and therapists to work. This is an area that I worked on a bit, is the length adjustment mechanisms for the upper arm and forearm. And these are just allow us to make sure that the robot fits the length of your forearm, the length of your upper arm, and in a precise way. So we have rulers there so that it can be done repeatably. Another area I worked on a lot was integration of our actuators and sensors. So we're using these harmonic drive actuators to drive all of the joints, as well as ATI force torque sensors at all of the interfaces between the user and the exoskeleton. Those measure how much you're pushing and pulling on the robot, and we're using those signals to drive our force control. Blue SABINO also has biomeasurement capabilities for EMG and EEG, like I mentioned. Just some pictures of us using those disposable electrodes. We can measure what's going on in your muscles and what's going on a little bit in your brain while you're using the exoskeleton. This figure shows the overall electromechanical system for the full Blue SABINO system. So there's a lot here, but we're using MATLAB Simulink real-time software from MathWorks to develop our controller. That's developed on a host computer, gets pushed to a target computer that is running a really fast control loop. So 1,000 times a second, it's sampling all of our motors and sensors and recording the states. So what is the position that the robot's at? What are the forces at? So we can use those signals for our analysis later. We also have at the hardware level some safety features. So a e-stop circuit and a safe torque off circuit that if you press one of those buttons, it can disable the actuators without having to go through any of the control or computer stuff. So if something is going wrong, we can turn things off. So that brings me to my research objective. My primary goal has been to create for this system a physical human-robot interaction environment that can assess and assist both healthy and impaired patients or subjects. To accomplish this goal, I've worked to implement an array of design improvements and I also studied a novel force control design and implemented it on the system. So now we can talk about those design contributions. So one of the aspects that I worked on was the mechanical hard stops. So this is kind of a safety feature. They limit the range of motion of the system. They're kind of a wide limit. So these have to be used in conjunction with software limits to really protect somebody from things like inner workspace collisions and that kind of thing. But we do know that extending beyond these limits is something that would hurt a person. So they're kind of an important thing. I've got another picture of some of the ones for the wrist here. Another use of those hard stops is as datums for our humming procedure. So they give us a reliable position that I can automatically turn the robot on and have it reach out and run into those stops. I know exactly where the joints are. So if I have to move the system and recalibrate it, we can use these. Like I said, we've designed Blue SABINO to accommodate as much of natural motion range as possible. So on the right, I've got a comparison of the range that Blue SABINO can achieve with these hard stop designs that I've worked on compared to healthy capabilities just for anthropometric motions that are available from NASA's biomechanics database. And I've got some illustrations of those motions here. And what you can see is that SABINO is able to cover between the 5th and 95th percentile range for males, females for 10 of these 14 movements. And the ones that it can't completely cover are actually mostly involved with reaching behind the user, which isn't necessarily what we're trying to study with the system. But we still get a sizable portion of that workspace. Another area that I worked on pretty extensively is the human-robot attachment system. So this was something we wanted to create constraints between the user and the robot that are really a stiff constraint. So we want there to not be a lot of play between you and the robot so that we can have high force transmission bandwidth. They also need to be something that's comfortable to wear for extended duration of time so that you can do a lot of experiments while wearing the system and not want to discontinue because you're feeling uncomfortable or because there's pressure points from a orthotic pushing into you. We needed to incorporate adaptability so that we can fit the cuffs to a wide range of different users. And then they just needed to be efficient to take on and off, because in a clinical setting, we want to be pretty fast about getting patients in and using everybody's time efficiently. So here's just some examples of other systems trying to show what their attachment systems look like. Most of the devices that are out there use a pretty similar design where they have like a U-shaped base, can be a wider U channel or a pretty small U channel. And then they'll just have textile straps, normally Velcro or something that pulls tight to fix somebody in place. Some issues with that approach is that textile straps aren't necessarily very stiff, so you can get some, more play with that approach. And also, since a lot of these are kind of one size fits all designs, you end up with designs that if you have like a smaller user in the device, their arm is going to have to come a lot more out of alignment with the exoskeleton's kinematics when it gets kind of strapped in. So, and that can result in some limitations in their control bandwidth and some discomfort for the user. So some other ways that people have looked into trying to improve on that approach is using inflatable orthotics, putting in foam inserts to try and better center the arm, or just using custom molded thermoplastic designs. So sometimes they have these thermoplastics that they'll mold to an individual and fit in a device. But none of those approaches are super satisfactory for a clinical application because they require additional tooling or expertise to do. And in the case of that O-shaped ring, you can put too much pressure on somebody. But recently, the NEXO2, there's a paper they put out where they investigated a design where they incorporated some self-aligning and self-adapting features, and they found that it does improve the comfort of the device, their ability to remain aligned, and the overall control bandwidth. So it's something worth having. So for Blue SABINO, I opted to investigate 3D printed orthotics. This is kind of illustrating the workflow that I went through. We did a bunch of laser scanning of actual human topology, imported that into our CAD, and designed orthotics that closely match the actual geometry of an arm. I went about 2 different ways of trying to incorporate adjustability. So the first simplest approach is just to have solid body parts, but just print enough different sizes of them that they work for a wide range of different users. So these models that I developed have at the base part of their design tree a scalable feature that you can that correlates to different anthropometric sizes. So you can just change one number and scale them up and down. But if you don't want to switch out orthotic parts, which is kind of for time efficiency, I developed a size adjustable design. So this has an integrated slide in it that allows you to actually change the width of the orthotics just using a thumb screw. So this is a toolless design. There's springs embedded in there that help them expand. And there's also some locking thumb screws so we can lock their positions. This just is some of the pros and cons of each of those different approaches. The solid body designs are probably the most mechanically simple. They're the more lightweight option. They, if you use enough sizes, could in theory have really, really precise kinematic alignment. but you'd have to probably measure a patient in advance to choose the right size. And then you have to use tooling to change them out, unless we go in and add some quick change things. So we're using the size adjustable ones now because of the added convenience of being able to just set somebody in the exoskeleton and quickly set it to the right size. But that does have some increased weight complexity. And then some other things I'm not going to talk about for the sake of time, but I worked a lot on the wiring design for the system, the external harness, and all the electrical components, integrating them and putting them in a housing where they'd be safe. And I also work a lot on the 2-degree of freedom design, which we actually took up to St. Luke's and did some testing with stroke patients with. So moving on to my work on the kinematics and force mapping. So this, I worked on the kinematics is taking the joint positions of the robot and mapping it to Cartesian locations on whatever end effector that we're interested in. To define them, you have to decide, set a home position for the robot and say where all of the joint axes are located in space and what all of the orientations of their rotation axes are. And that's just what this picture is showing here. And something to note in the math that I did for that, I included the width of your shoulder, the length of your upper arm and forearm as parameters, so you can use the same model for a bunch of different sizes of people, and you'll still get accurate spatial positions for whatever you're interested in. Another thing I worked on was developing body manipulator Jacobians. These map the forces that a user applies on the exoskeleton to joint torques. So they're kind of like a statics solving a matrix thing. So you take these forces that we're applying and it becomes equivalent torques at each of the joints that we can use in our control scheme. And to develop those, we just had to define where are the sensors in the home position, what are their orientations. And that's what these figures are showing. I also worked on making a gravity model for the system. And that kind of depends on knowing where the centers of mass of all your parts are. So to get a list of where all those are, I went in SolidWorks, assigned mass properties for everything. Went through the whole process of recording all that. I'm just plotting that in MATLAB here to show we got those positions right. And then to validate some of the forward kinematics, I've got an animation here. This is not done in SolidWorks. This is a MATLAB-based animation that's using my forward kinematics math. And the fact that things are moving kind of the way that we'd expect, like they're mated together properly and not flying apart, is a good indicator that we got our forward kinematics right. To validate the Jacobians, we did some simulation and just evaluation of if you put in X force, you're going to see the joint torques you'd expect. But kind of the true test that everything is right is you can put it on the robot, use it for control. And so you push on those axes and everything moves and the robot responds very naturally. So here's me just using a force control mode with those Jacobians on the 5-right system. Kind of fun. Okay, let me talk about my force control work. So there is, like I said, evidence that patient engagement is really critical to improving therapy outcomes. We know that patients benefit the most when we have higher duration and intensive therapy, and when the challenge level or the assistance that we're providing continually changes to match their demonstrated capabilities. Robots are really good tools for promoting engagement using assist as needed techniques because they can automate that measuring the patient's capability process and modulate the assistance that we're giving through it. However, in order to build a really effective assist as needed control, we'd really like to have force controllers for robots that can render high transparency, and particularly high transparency free motion, so we can emulate tasks that you do in a rehabilitation setting. Ideally, a transparent control would make the robot feel really invisible. So when you don't need assistance or resistance from the system, it would be like you're really just not wearing it at all, and it'd just be really light to the touch. Obviously, there's some reasons why that's difficult to do because the robot actually does have inertia and all these other dynamics that we have to compensate for. But it's still important to try and get as close to that as possible. And some reasons for that, we know that if the robot isn't transparent, it can affect the motor patterns that a person uses to move. And if we want to be able to use these for assessment, we really need to get as close to naturalistic motor patterns as possible. Okay, so rendering free motion is a challenge for rehab robots, mostly because they have relatively high weight, powerful actuators and structures so that they can support your arm and provide assistance and strength training, that kind of thing. Underlying challenges include that it's harder when you have a lot of gearing to measure and or estimate what human motion and tension is versus some other disturbance in your system. There are always uncertainties in the robot dynamics. So if we have unmodeled friction or inertial effects, those can kind of mess things up. And then if there's any kinematic misalignments between the robot and user. Most systems use an admittance or impedance approach to the control to achieve high transparency. Most of the time, we try to model out as many of the dynamics as we can, so we compensate for what we know well, and then you use state feedback to try and mask out the rest. And then what admittance and impedance control really do is they just add back in a little bit of dynamics most of the time to stabilize the system. So you have a little bit of resistance, try and get rid of everything and just get a little bit of resistance that makes it nice and stable, but not take a lot of force to move around. So in my literature review of different systems, there's a couple of different approaches to trying to improve transparency. The first one that's playing here is the Limpact system. Play that again. They use hydraulic actuators and self-aligning components, as well as a really lightweight structure to try and make it transparent. Exoskeleton 8 is shown here. They did a study where they tried to use a couple different control approaches, but Kalman filtering to balance out the forces that they're reading from the sensors and try and make it more natural feeling. Any Exo here, they use series elastic actuation and had a bunch of inertial measurement units and stuff, and they actually do their feedback linearization and acceleration to get that control result. I tried to categorize some of the ways that you can go about making force control more transparent here. So I've got it kind of divided into, you can improve your ability to sense motion and tension. You can try and compensate for things better in your dynamics. So you go in and do some identification, or you could even try to adaptively compensate for dynamics. And then the other way is to try and improve the render dynamics that you're adding back in. So I'm going to talk a little bit about adding in some terms that improve the ability of admittance control to reject disturbances. So this is our control loop. So this is just for a single joint, but this consists of, this control loop consists of a outer force loop. That's what the admittance control loop is. It receives the forces that have been mapped from our Jacobians as joint torques and uses that knowledge and knowledge of where the robot is at to try and set a target for the robot to go to that will try and reduce the amount of force that's being applied to the robot in the next time step. So then it sets that target, that gets sent to our inner loop. We try and get the inner loop set to really precisely track the target trajectory. And of course, we have a little bit of, like I said, gravity, we have some compensation going on. So we're using gravity and friction compensation. This is just the robot's dynamics stated as an equation. You normally see there'll be an inertial and Coriolis term. We're actually kind of neglecting to compensate for those right now because at most rehabilitation movement speeds, your inertial forces aren't actually very big. Instead, we focused on gravity and friction because those are really dominant in our system. And then tau U, there is the control input. Tau H is the human applied forces. So here's just the control law that we proposed. If we put that into our dynamics equation and we suppose that we did a really good job at compensating for our gravity and friction, that reduces down to this, where we just have our whatever inertial forces there are left, whatever the forces that the human is applying, and then a proportional and derivative term. And so the Kp and Kd terms are doing most of the work on masking whatever nonlinear dynamics are left. This is just showing what the gains that I use for Kp and Kd are. I've already said we try to make those really, we try to make the inner loop tracking really high bandwidth because in turn that helps us to maximize the force bandwidth. To benchmark the performance of the inner loop, I did some sine wave tests where I input a sine wave trajectory. I'm going to show you the results just on the steady state portion here, but this is a 1 Hertz trajectory that I'm asking the robot to track, and it's like 10-degree amplitude. This is looking at it from kind of a state space perspective. So we have position on the x-axis and velocity on the y. And then there's like a dashed black circle that's like what the ideal tracking would have been. I've got a little animation there showing like how the states would progress as we went around the circle. And for each of the joints, we're getting really close to tracking that circle. Joint 5, you can see a little bit of some excitation of dynamics going on. So there could be, the fun thing with friction is it's hard to tell whether we're overcompensating or undercompensating for it, but something's going on in that joint a little bit that we could probably tune up. But overall, we do have pretty high state tracking accuracy. I also did a chirp tracking experiment. This is a logarithmically spaced chirp that we put in that's going from frequency of like 0.1 Hertz to 2 Hertz over the course of 75 seconds. And this is just to benchmark performance over a range of different frequency inputs. So we're seeing that overall our error, our root mean square error for each of the joints stays under a degree. Things do get a little bit worse as we go faster because those inertial terms are starting to matter more, but 2 Hertz is faster than pretty much most motions we expect to see. So this is a pretty good result. And our velocity error also is remaining under 10 degrees a second. Just looking at the beginning and end of those chirp responses here, we can see what the torque requirement on these last graphs are. And the main thing to notice is that when we get up to 2 Hertz, we're staying within the continuous torque band for most of our joints. The base 2 or 3 are getting out into maximum torque band. So that's a range where the actuators can supply that torque for a limited amount of time, but they can't do it continuously or they'd overheat. And then the main thing is that the base joint is starting to get into that range for a little bit longer than it's probably ideal. So if we keep adding weight to that, we might need to consider putting on a spring balance or something to better center it, but better center the load on it, but nothing too concerning here. Okay, so this is the admittance model that we use on the next slide. So I'm just going to keep going. So like I said, I'm trying to improve the dynamics that I'm adding back into the system to help it reject disturbance. It's not really clear how you should go about doing that from the literature or what terms you should use. So we can use inertial terms to try and make it feel like it's got more inertia, or like a damping term to try and take out energy. In general, the more impedance you add in, the less transparent it's going to feel. So you like to try and minimize how much of these terms we do. To investigate what the effects of the different some different approaches, I've tried 4 different modes. So I have a low mass mode where I just have a low amount of inertia in here. I have a high mass mode where I make inertia pretty high. The velocity damping mode will make it feel more viscous. We just have a kind of continuous damper, and a velocity air damping mode that's kind of monitoring the difference between where the admittance model is saying the velocity should be and what it actually is, and using that to turn up and down at the damper, basically. The damper is always present, but it kind of feels like a damper that just appears when there's velocity tracking error. And the idea there is that if there's velocity tracking error, something we don't want to be happening is probably happening, like vibration or yeah, pretty much vibration. I should say here, I think I have a slide that comes up next, what those different terms are in the model. So M is the inertia, B sub V is a velocity damping term, and BVE is a velocity air damping term. And these are the values I used in these experiments, the units on them.
So I'll explain the model just a little bit more, like explain what the how sub H is.
Oh, so yeah, so
how basically the mapped human torque is producing desired states.
okay, so what we're on this side of the equation, which some people probably can't see, so I don't use it. Can you guys see my mouse?
Yeah, do that.
Okay, good. So on this side of the equation, we have, this is like an input vector. So we're taking in what's the measured position, measured velocity, and the measured human applied torques, and using that This is like a, if you,
At the joint, for each joint.
yeah, for each joint. Yeah. So we're only looking at, this is like a progression for one joint. So this is like how the input can affect the output basically. So if we're putting in, it's hard to not just walk over there and point at it. So that tau H term, it's going to end up multiplying with the inertial term, right? So if we turn up the inertia, that ends up kind of filtering how it's 1 over, so it's dividing it. It's going to filter how much your input forces matter, right? So it'll make it so that input forces are not driving the system around as much. We have some filtering on velocity with the velocity air damping one. And then the first matrix there is just taking the desired state and the desired position and velocity, multiplying those by these dynamics. So we pass through what is the current position and what is the current desired velocity. The current desired position is going to get a added version of the velocity. So it's kind of like a Euler integration where we're looking at what is our current position, what is the measured velocity times these dynamics to set what is our next target position. Does that kind of clarify things?
We have to try to tweak your answer one more step just for everyone's so if I go to forces and go to torque, might be a little easier to understand. This model says if you push on the robot sensor in a certain direction, what does it do to the desired position of the robot?
So if you push on it in a certain direction, it keeps, yeah, okay. So if you push on the sensor, it's going to keep driving the position a little bit further away from where you are. So the next time step will keep dragging you. So it's kind of like if you put if you did this purely inertial, so if you have no damping or anything, you can push on the sensor and it will keep driving like the target position away. And if you have more inertia, it'll like make it harder to push that target position away, kind of thing. The damping is like a friction on where is the target position. Yeah, the velocity error one is like we tie the position of measured position and the target state position together in the velocity state. You can also, there's other ways we do this. We could put like a spring term or something in there, but we're just investigating these ones for now. But okay, I did some experiments to test these different modes out. So the two I'm going to talk about is this high repetition motion task where I just drive the robot back and forth between the home position and a target, get a lot of repetitions of it. And the other one is a low repetition distributed motion is what I'm calling it, but I'm going between throughout the different workspace, the different targets. You can see in this animation, there's a couple visual aids in this environment that's on a TV in front of me while I'm playing the game, so I can see where I'm supposed to be moving the robot to. We have a green cube in my hand that'll turn green it's red when I'm not aligned, but when I bring it into alignment, it'll turn green. And then I've got a clock there that's trying to, it'll fill up when I'm supposed to arrive at a target. So it's trying to help me get my timing back right when I'm moving. There's also some audio cues going on. So there's like a beep, a metronome kind of sound that's telling me when to arrive at a target. I did some frequency analysis to the data from the distributed motion task. And my goal of this was to figure out what the variation in the frequency content is throughout the workspace of the robot. And when I'm talking about frequency content, we're really talking about how much does it pass through frequencies that are associated with a human's motion, and how much is it eliminating frequencies that are vibration so the process, I'm doing segmentation by different targets. This Welsh estimation is kind of like taking a FFT of I should say I'm using the measured torques from the human. Yeah, the Welsh estimate is like taking an FFT of that data and kind of figuring out how much power is in each frequency band. It's a little fancier than that, so I end up with units of power and a smooth estimate, but that's really it. And then I'm averaging results back together to do some statistics. So like I said, I'm trying to get a sense of what the performance is throughout the workspace, but I also did it to figure out what the overall performance is. And this is kind of the result of that. One of the results of that analysis. So this is an overall result for the whole workspace. So we're looking at frequency versus power on the top graph. And I've got annotated here some different motion bands of interest. So we know that human motion is going to probably be between 0 and 5 hertz. The most part, it's actually going to be quite low, like between 0 and 2 hertz. And then 5 to 10 hertz is kind of associated with the system resonance. We know it's probably somewhere between 7 and 8 hertz, depending on how the robot is oriented. 10 to 500 hertz, we can kind of sense some of that, but it gets to be like a high buzzing feel. But anything in the 5 to or greater hertz range is something that we pretty much want to regulate down. We want to make the stuff between 0 to 5 hertz higher because we want to see more human frequency and none of the rest of the stuff. To make the comparison of the different modes a little easier here, I normalized by the low mass mode. I did that because the low mass mode is kind of the worst mode in terms of vibration. Just doing the experiments, I could tell that one's vibrating the most. And you can see all of the other modes reduce the power in the 5 to 10 hertz range for that. The velocity error damping and the high mass modes are shown here in red and yellow are doing or allowing the most low frequency content through. So they're probably performing the best in terms of frequency. This is just summarizing those frequency charts as it's basically integrating the power between the different bands. So like I was saying, we want to see higher values in low frequency and lower values in high frequency. And we're, for the most part, seeing the velocity error damping is doing better at rejecting disturbance. High mass is probably doing better at allowing low frequency content through. And then here's those results plotted over all the different positions. We can see this is just for the 5 to 10 hertz range. So the one I'm trying the hardest to make smaller. We can see that one of the nice things with the velocity error damping here is like the damping mode as well. They're both having way less variation throughout the workspace. The high mass, both of the inertial modes have a lot more variation, and it seems to be coming from reaches out here in this right region of the robot's workspace. Another way I went about characterizing performance is some spatial temporal analysis. What we're really doing here is trying to determine how natural your motion was doing a reach and return task. So this is using the high repetition data where we're just going to one target. The process is somewhat similar. We're segmenting by mode. I performed that experiment at 3 different motion speeds, so a slow, medium, and a fast speed. And then we're going to characterize naturalness by fitting a minimum jerk trajectory to the recorded data and seeing how close we can get those two, which I'll show a little more on the other side. So minimum jerk trajectory, we kind of actually know that humans move in this minimum jerk fashion most of the time. We do that because it kind of minimizes the amount of energy we're expending to do a motion. A minimum jerk trajectory kind of looks like this S-shaped curve in position, and the velocity state kind of ends up looking like a Gaussian type function. So that I'm showing that as these blue lines here. And how we went about fitting this to our data, we used FMINCON, and we gave it 4 parameters that it's allowed to set for this trajectory. So it's allowed to decide. What's up? Oh, it's an optimization thing in MATLAB. Thank you. Yeah, so we're deciding where the minimum jerk trajectory starts moving, what time it stops moving, and what time it starts moving, what time it stops moving in the starting and stopping position. So it's allowed to kind of adjust that S-shaped curve, position, and height and all that stuff to get it to match up to the data as well as it can. And then I'm just adding up all of the error and to decide how much different basically the measured trajectory was from an idealized one. This is kind of showing the over all of those different repetitions I did, what the distribution of results are in terms of naturalness. The main things to notice here is that it's kind of velocity dependent, which mode is allowing the most natural motion. So the low mass mode is exhibiting the least error to a minimum jerk trajectory for like slow 2-second motions. The high mass mode is probably doing the best on the 1-second motions, and the velocity error damping is doing the best for fast motions. But they're kind of got some close together ones too here. So, okay, and then one last way that I want about characterizing performance is how much work is happening between the user and robot. So an important feature is that we would like you to be able to do as little work as possible to do the task, but also to have as little work done on you as possible. So it would be transparent if you're just driving your arm and that you're supporting yourself. So I evaluated the instant work on each of the joints and added those up. Just can get that by measuring what is the joint torque applied by the human and multiplying it by the velocities of each of the joints. I've got plotted here on the top the instant work versus time for each of the different motion tempos that we did. And then I also characterized it by taking the absolute value of the work and integrating it. So just coming up with how much cumulative work was done over time. And here we can see that the velocity air damping is probably performing the best overall. Velocity damping is doing pretty poorly here because you're having to continuously push on that damper to move throughout the whole workspace. Yep. And just to kind of wrap that up, so we found that in general, the velocity air damping mode is able to improve transparency. So it can reduce the work and vibration content and improve naturalness for some motion speeds. The performance, especially in terms of naturalness, does depend on the characteristics of the task. So if you're moving quickly or you're moving slowly, like when you're moving quickly, it might actually be better to have these damping terms because they can help get rid of some of the excitation of the system. Moving more slowly, it turned out that the inertial terms are actually maybe better. Just because you don't have to do as much work against that damper, you can push really lightly and get the robot to start. So for some future work coming from this, we might consider adding some metrics that are more useful for stroke assessment, like smoothness. We could also investigate trying to leverage our understanding of how the different modes or how those different terms benefit motion by transitioning between different combinations of terms depending on some knowledge we have about the task. So if we know we've been moving slowly for 10 seconds, maybe we can use a purely inertial mode and start turning up the damping when we know our speed is going up. And now I'd just like to try and complete this presentation by talking about overall summary of contributions and some areas for future work. So I talked about my work on making design improvements to the system, including adding hard stops, making it the human robot attachment system for the device, and some of the modular wiring, other components that we put in. Those printed size adjustable orthotics, we've investigated two different approaches. I found that both facilitate minimal misalignment and can create a strong, comfortable interaction between the exoskeleton and user, but I like to use the size adjustable one for the efficiency. And then we developed the kinematics for the system, talked through the transparent force control mode, and importantly demonstrated the efficacy of that velocity air damping mode. So some areas for future work, we could investigate improving the human robot attachment system further by probably adding some more contacts for the upper arm and forearm. So there's a couple other examples of robots that do that, but as we add more joints, we're going to have to rely on our wrist joint, our wrist force sensor less. And if we want to use or better leverage or get more moment arm basically on the force sensors for the forearm and wrist, adding a contact at the upper and bottom could help us do that, but we could also just work on where we're positioning those. We could also, like I said, work on putting in variation in our remittance control or implementing adaptation and what those dynamics are. And then a little further out there, we could also look into adding some different or additional sensors so that we have ability to better estimate human motion and tension or knock out the dynamics of the rest of the system so that we can improve the transparency further. But And that kind of brings me to the end of my presentation. So thanks everybody for your time and attention. If anybody has any questions, I'd be happy to try and answer them for you. But...